SwayamPrabha. Digital India. Educated India.
Welcome back. So, this is lecture number 3. We will continue from where we stopped in the previous lecture. So, if you recall, we had talked about the velocity, efflux velocity Vj was dependent on various parameters. So, if you recall, the equations we got for Vj was square root 2 gamma R u T c gamma minus 1 into molecular weight into 1 minus P e by P c to the power gamma minus 1 by gamma. Now, if you look at the equation carefully, in order to have very high jet velocity or the efflux velocity, we need to have very high combustion chamber temperature, or the high value of T c is essential. So, the propellant which can generate very high temperature is going to be beneficial for increase the Vj, because Vj has the direct influence on the incremental velocity delta V, which we have already seen in the rocket equation. What about the Pc? Pc must be high, because you see it is P by Pc to the power gamma minus 1. So, in a sense we can say in order to get high Vj, we need to have high Tc and high Pc, or high chamber temperature and high chamber pressure. The molecular weight of the products will have negative influence, like the reverse influence, like the increase in molecular weight is going to decrease the value of Vj. So, we want the molecular weight of the products to be in the lower side, so that it can give the higher Vj or higher efflux velocity or higher jet velocity. Now, the gamma value has some weak influence, which one can see through some parametric studies, like taking various values of gamma, keeping other values constant, and see how the Vj is going to vary. But eventually, if you look at the major influencing parameter here are the pressure and the temperature. So, we can expect that high value of Vj will take place when the combustion of the propellant gives very high value of chamber temperature and at a high pressure. So, the combustion should take place at high pressure, and it should generate very high temperature. Now, I am just referring some of the plots given by Professor Ramamurthy's book, which you can get the exact value, but I am just showing only the trends here. Like if you plot Vj versus chamber temperature, which you can try varying from 300 to let us say 4000 or so, 4000 Kelvin. So, this is Tc in Kelvin. So, you can refer Professor Ramamurthy's book on rocket propulsion. It is already mentioned in the course document. So, if you look at the velocity of efflux or the jet velocity, which we can just get it from various ranges starting from let us say 500 meter per second. So, it is in meter per second, and it can go as high as like 4000 or so. So, I am just giving you the trend. So, the Vj is going to increase with the increase of chamber temperature Tc. Now, if you see the same plot for same effect of Vj with respect to the molecular weight, we may see that the increase in molecular weight is going to actually decrease the value of Vj, and that is evident from the equation as well. If you look at the equation, it is like 1 by square of 1 by molecular weight. So, the Vj is going to decrease if we have the molecular weight increase in the products. So, in a sense, if we have like a complete combustion of propellants, which will give us the higher value of molecular weight, that is not conducive in order to generate high value of Vj. So, in many occasions what is done, slightly fuel rich mixture is used in order to use these advantages of lower molecular of the products. You can take a quick example, like if you burn, let us say, some hydrocarbon CXHY plus O2, and you are forming, like if it is a complete combustion, then it is going to give you CO2 plus H2O. I am not balancing the equation, just to give you a glimpse of it. But if it is not a complete combustion, then it can have, like, let us say this is y amount of CO2, this is y1 amount of CO2, y1 amount of O2, this is going to give CO plus CO2 plus H2O. Now, if you consider the average molecular weight of these combustion products, you may see slightly incomplete combustion is going to generate some CO, because CO has a lower molecular weight compared to CO2. So, on an average, this is going to give us slightly lower molecular weight, which will give us the advantage in terms of increasing the velocity Vj. So, in many occasions, the mixture ratio is made slightly fuel rich in order to have the Vj. We have just talked about in terms of Vj, but later on we will see that the specific impulse, which is one of the important performance parameter, is actually very much related to Vj, which is actually in a similar unit is actually equal to Vj. So, in a sense, we can say the performance of the rocket will very much depend on these things. If we can increase the combustion chamber temperature Tc very high, if we lower the molecular weight, that will be conducive to generate high jet velocity, or in a sense to increase the rocket performance. Now, if you look at the influence of the gamma, because this is another influencing factor, gamma has a weak influence on the efflux velocity or the jet velocity. So, higher the value of gamma can have slightly lower value of Vj, but overall it has negligible effect, you can say. So, the major effect is played by the chamber temperature and the molecular weight, you can say. Okay. So, I think with that we can understand the influencing parameters which are important for Vj. Now, we will proceed further and we will try to understand various performance parameter of rocket, which we already learned probably in the previous course, but as I said earlier that the first module of this course will just give you some glimpse of what you have already learned from the basic course of rocket propulsion or from the aerospace propulsion, and we will try to just revise some of the stuffs just to set the floor. So, once we talk about the performance parameters, we will first talk about the very important parameter, which is thrust. Now, if you recall the thrust equation for turbojet engine or the air breathing engine, we had written the thrust equation as F equal to m dot exit into some exit velocity minus m dot A, you can say, into U A plus the difference in pressure, exit pressure minus ambient pressure into the exit area of the nozzle. This was your equation in case of turbojet engine or air breathing engines, because we have some inlet flow stream which has the velocity U A and we had some inlet mass stream m dot A. But for a rocket, since it is carrying its own oxidizer, there is no inlet mass going into the rocket, or neither there is any inlet flow stream going into the rocket. So, we do not have this terminology in the thrust equation of the rocket. So, if you look at the thrust equation of a rocket, we can simply write F equal to m dot into, we just write the jet velocity as Vj, because we have already used this terminology from the beginning. So, let us be consistent with that. It is m dot Vj plus Pe minus Pa into Ae. So, how we are deriving this equation? I will just give you a glimpse of it, that if you take this a simple schematic of a rocket. We have the exit area AE, the ambient pressure is working all around the rocket. So, this is the ambient pressure, so this is PA. So, here it is also PA, ambient pressure. The exit pressure is PE, throat area may be AT, chamber pressure can be PC, chamber temperature can be TC. The chamber pressure again internally it is acting on inside the rocket everywhere. Here of course, your pressure will be changed because here the throat is there. So, it is so this part is throat, this is the combustion chamber, and this is the exit of the nozzle. Okay. So, from here we can actually try to figure out that how we can get this equation, that since there is no flow going into the rocket. So, this part is missing. If you look at this equation number 1 and equation number 2. So, this is from your turbojet or in general the air breathing engine. So, this is the air breathing engine. So, this part is missing because we do not have any external the mass stream going into the rocket, neither the velocity. So, we have this straightway this equation. Now, what we can say about these two terminology, the first one and the second one. The first one is the momentum thrust and the second one is the pressure thrust. Okay. I guess this is known to all of us. So, the first one is the momentum thrust, and the second one is the pressure thrust. Okay. Now, if we say that my vehicle is going above the sea level and is going up in the altitude. So, your PA is changing. Okay. PA is the ambient condition, because PA we do not have any control. So, as we go up and up, your PA is reducing. So, there may be some situation towards the lower altitude that your PA the PE is less than PA. So, it may be this term may be negative. So, it has the negative effect. So, if the PA is greater than PE, it will be the negative effect. So, that is sometimes not desirable. Also, it has some influencing factor if your flow is not going to expand optimally. So, in a design condition, we always say that P is equal to PA. I think you must have already learned this thing, that for the optimum expansion we say that, and that is more desirable. Anything out of it will be like undesirable. So, that performance will be low, but there are conditions where absolute vacuum conditions, where you can say the ambient pressure is 0. So, your thrust equation become m dot Vj plus Pe into Ae. So, that is for case of vacuum. For optimum expansion, we can simply say P equal to Pa. So, our thrust equation will become m dot Vj. In many occasions, we are going to follow this optimum expansion case where P is exactly equal to Pa. So, there will be no momentum thrust present. We can simply write F equal to m dot into Vj. Now, let us say other performance parameters. So, thrust, we begin with the thrust. Now, we can say the total impulse. Total impulse is denoted as IT, which is the integrated over the time duration F into T. For a constant thrust, we can simply write the total impulse equal to F into T. Now, one of the important parameter is called specific impulse. which is denoted as ISP. In some book it is referring as only IS. So, we are referring it as ISP. This is the total impulse per unit weight of the propellant. So, we can just simply write this as total impulse F dt into m dot t. So, if there is any transient effects like stop and starting, there is a change in the flow rate, we can actually get the total mass flow total mass of the or total weight of the propellant by integrating this, and the total impulse we can get it from there if there is a variation of thrust. But for constant thrust and constant mass flow rate of propellant, we can simply write ISP as total impulse by propellant mass into G0. So, we can say propellant mass here. Now, if you see here that in case of like a higher altitude or outside the gravitational field, so what is the meaning of this G0? Here we are considering the G0 as the gravitational constant, but acceleration due to gravity. So, what about when there is a outside of the gravitational field? So, in SI system we can say the ISP is expressed, just to make this ISP in second. If you look at the unit here, it will be just in second. In order to do that, G0 is considered to be an arbitrary constant with a value of course 9.81 meter per second square. This is equally acceptable for outside the earth gravitational field, just to make sure that ISP unit in second. But there are other way of defining it also, like we can write this ISP as total impulse by the propellant mass instead of the weight. That will give us, it will become Ft by mp, which will nothing but F by m dot p, which is nothing but the Vj. If you recall, we had the optimum expansion case where in ideal situation we always consider this part, that P is going to be equal to Pa. So, we have the thrust equation as F equal to m dot Vj. So, we are considering that, and we write down the equation for ISP in terms of total impulse by mp, which is becoming like F by m dot, which is eventually become Vj. And once we have Vj, this has the unit of velocity, which is meter per second. Okay. So, this is another way of expressing the specific impulse. Now, what about the other parameters we can keep deriving? So, one such important parameter is the, it is called the characteristics velocity. So, remember ISP is kind of an important parameter as we consider the vehicle, like the ground transportation like car or automobile. So, they have how much mileage, like how much kilometer it's giving per liter of petrol or per liter of diesel. So, it is similar to in a rocket literature, it is a similar concept that ISP is an important parameter. Another important parameter is called characteristic velocity, which is denoted by the symbol C star. So, now let us try to derive the equations for C star in terms of other parameters. So, we will begin with the derivation of this C star by considering the mass flow rate through the throat of the nozzle. As we have already derived the equation for Vj, we can use the similar manner. We can just simply consider the mass flow rate through the throat of the nozzle. So, if you just consider that, we can simply write that if the throat area of a nozzle is At, the density of the gas is rho t, the velocity of the gas at throat is Vt, we can simply write m dot or the mass flow rate through the nozzle throat is going to be equal to rho t into V T into A T, where rho T is the density of the gas at the throat, V T is the velocity of the gas at the throat, A T is the throat area. Now, what we can write about the density? We can express density in terms of pressure and temperature. So, we can write P T by R T T, and you may recall that from our ideal rocket assumption, we can use the perfect gas law, and we can use various equations we used for isentropic flow through nozzle. So, we can actually apply some of the equations. So, if we apply the perfect, we can assume perfect gas and steady one dimensional adiabatic flow in the convergent portion of the nozzle. We can simply write the, I am just writing from the previous equation. I mean, we already did it for the derivation of the V J. So, I am just writing the same thing for considering the throat. So, what I am writing here, if you just recall, we had something like this. So, if this is your converging part, so it is P C, T C, V C, here we have A T, we have V T, we have T T. So, this is the throat. Okay. So, we are writing this part. So, if you just write the steady one dimensional adiabatic, considering one dimensional adiabatic flow, we can simply write H C plus V C square by 2 equal to H T plus V T square by 2. We can take out this part because this is almost negligible. So, we eventually get H C equal to H T plus V T square by 2. What about H C? H C you can write in terms of C P into T C plus C P into T T plus V T square by 2. This we can write in terms of other parameter, like for example, like we can use the Mach number here, but let us first simplify a little bit. So, we can just write T C equal to T T plus, we can divide by C P only. So, this will become V T square by 2 C P, which we can simplify even further, 1 plus gamma minus 1 by 2 gamma r T T into V T square. We just simply replacing C P as gamma minus 1 by gamma into r by gamma minus 1, that we have replaced for C P. Now, we know that the sonic velocity is A T, which is equal to square root of gamma r T T T. So, sonic velocity at the throat will become square root of gamma r T T, which you can see it is here. So, it is nothing but we can say it is A T square. So, this will become T T into 1 plus gamma minus 1 by 2 into V T square by A T square. So, what about this V T square by A T square? It is nothing but the Mach number will be M T square. So, we can write this as T T into 1 plus gamma minus 1 by 2 into M T square. Now, if you recall, we assume the value of Mach number at the throat is 1. So, eventually at throat we have considered the Mach number equal to 1. So, this equation will become T C equal to T T into 1 plus gamma minus 1 by 2, which will eventually become T T into gamma plus 1 by 2. Okay. So, this is one important equation. So, we can just give this name as equation number 1 here. So, after deriving this, now if you considering the isentropic expansion process in the nozzle, what you can write? We can write, rather we can just go back to this equation. Instead of giving this equation number 1, we can simply change this, and we can say this ratio T c by T t equal to gamma plus 1 by 2, and that we can say equation number 1. Okay. Now, let us go to the next equation, which we can write the isentropic expansion process in the nozzle, and we say P c by P t equal to T c by T t to the power gamma by gamma minus 1. Okay. And we can now take this equation 2. Now, let us go back and look at this mass flow rate equation. So, let us consider this equation as A. So, we just put the value of this T c by T t, the density equation, let us say this is B, and we have 1 and 2. So, we can consider all, and we can put in the equation of mass flow rate, and we can write down the mass flow rate as, we put everything together, it will become square root of gamma into P c into A t by R T c into T t by T c to the power gamma plus 1 by 2 into 2 into gamma minus 1. Okay. So, we can express this in terms of, we take this gamma value other sides, and we can write this as what we can write here? We can write here is at P c by R T c, and rest of the term like square root of gamma into this T t by T c we already got earlier. So, we just express that in terms of gamma only. So, this equation will become like only a function of gamma, this part. Okay. So, this part is denoted as the capital gamma, and we can write this. So, this part is denoted as the capital gamma, and we can write this as gamma P c A t by R T c. Now, if we look at carefully this R T c by capital gamma, this, if you look at carefully the R T c by capital gamma, what about the unit of this one? One can actually look at the unit of this one, and we can see the R is the universal gas, the gas constant for the particular gas. So, this will be like joule per kg Kelvin, T is the temperature, joule can be divided into, joule can be further expanded into Newton meter per kg, Newton meter, then per kg will be there, Kelvin will cancel out, then finally, this will have a unit of meter per second. One can try doing it and easily find out that this will become a unit of velocity. So, eventually, this part is actually coming as a some kind of a transfer function we can say, which is relating the chamber pressure and the throat area with the mass flow rate. So, this term is called the C star or the characteristic velocity. So, our m dot is becoming related to the chamber pressure and the throat area with the transfer function C star or the characteristic velocity. So, this is another important equations we use time to time in case of rocket calculations, various calculations used in rocket performance. So, C star will become 1 by capital gamma. We can write R as universal gas constant R u T c by molecular weight. Okay. And of course, this is a velocity. So, the unit is meter per second. So, one can actually see how the temperature is going to influence the C star, how the C star is getting affected by the chamber temperature, and one can easily see the high temperature means C star's value is going to be very high, and of course, the C star is going to indicate the the potential of the propellant to generate hot gas. So, of course, the various propellants will have a different capacity or the potential to generate hot gas, and accordingly the C star value will be different. So, we can say this is kind of a index of performance. It consider as an index of performance. Okay. So, this is another important parameter we should consider while considering the performance parameters for rocket. Okay. And one can of course try looking at various chamber pressure, keeping the chamber pressure and AT constant. Then we can look at the C star, how it is influencing. One can get the value of various C star value for a constant gamma with a variation of chamber temperature. Okay, with of course, the specific heat ratio gamma will have some weak influence on the C star, but the T C has a major influence, and of course, the molecular weight. So, we can say the C star is also having the similar type of effect of the T C and MW, as we said, as we have seen already for the case of Vj or the jet velocity. So, basically the molecular weight, lower the molecular weight will give the higher C star velocity, as you have seen for the case of Vj. The higher the chamber temperature will give the effect of higher C star velocity. So, increase in T C, decrease in molecular weight will has an positive influence or is going to increase the C star. So, I think with that we stop here today. We will continue with this next topic of this part of the module in the another lecture. All right. Thank you.